Hello, Sorted Upper Fifths. Welcome to a little conversation about formula types. So we're going to go over displayed formula, structural formula, which is a wide-ranging definition really, and skeletal formula. And skeletal formula is probably the newest one, although you might well have mentioned it at GCSE at least. So these, let me show you this top one, nonane here. This nonane, this is an example of a displayed formula actually, because you can see every single, and it needs to be every single covalent bond is drawn in with the stick. Every one of those sticks shows that there's one single shared pair of electrons between the atoms, and because every single bond is there, it's an example of a displayed formula. Okay, so what other kind of formulas are there and why do we use them? So I think the one that you probably see quite a lot is a structural formula. And the reason we use a structural formula instead of a displayed formula is to stop us from going crazy, because drawing displayed formulas is a lots of sticks and it gets very annoying. So structural formula is a way of shortening it, and you can put it into a sentence as well, because it's kind of the same. It's linear, if you like. So on structural formula, look at every carbon as you go, every single carbon, and just say what's on it. So the first carbon here is there. It's got 3 hydrogens. That's supposed to be a 3. And then the next carbon, so another carbon. And then you go, okay, well, what's on that one? Well, it's 2 hydrogens. And then you go on to the next one. Okay, what's on this one? Well, another 2 hydrogens, CH2. Okay, and this one, CH2 again. This is a boring molecule, isn't it? And then another one, a CH2. And then another one, CH2. So it's a bit quicker. Another one, CH2. Here I'm worrying that I've run out of counting or something, so I'm going to count 1, 2, 3, 4, 5, 6, 7. Nonane is 9, so one more CH2. That one. Woo! Just go back up there. There we go. One more CH2 and then a CH3, because the last carbon's got 3 hydrogens on it. So you can see it's quicker than drawing out every bond, but it's still not ridiculously quick. And this is where skeletal comes in. Now, skeletal formula, basically, it allows you to do everything really quick, because all you do is you draw in the bonds between carbon atoms, and instead of drawing C every time, because most organic molecules are loads of carbon and loads of hydrogen, so you basically don't draw in the letters C and H, but you draw in correct numbers of bonds, i.e. single versus double versus triple, etc. And you draw in any other atoms that are not carbon or hydrogen bonded to a carbon hydrogen. So actually you do put in hydrogen atoms if they're bonded to something that isn't carbon. For example, alcohols, you'll draw the OH in. So you're going to see a lot of examples of skeletal, but I'll just show you how easy it is here. Okay, so you've got 9 carbons. So let's do it underneath the other one. So you've got carbon is technically a dot. And that dot, you don't draw the dot because you join it to another carbon, and then you kink to draw it to the other one, draw it to the next 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 one. And now I just double check that I've got enough, because am I drawing to the last one? I've miscounted again. So you just go 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 9 kinks or ends, so therefore it's 9 carbons in a row. And the reader needs to think, okay, well, if let's imagine we're looking at one carbon at the end here. Okay, well, it's got a bond to another carbon, because I see that, because I know that the carbon-to-carbon bonds are drawn in. I know carbon makes 4 bonds, so the other 3 things on it must be hydrogen, because if they weren't hydrogen, the skeletal formula would mention that. Okay, so we'll do lots of examples of skeletal formula. Let's just go down to this slightly more complicated one below. Just to look at its skeletal formula. A bit of this is actually technically skeletal already. If you look at that carbon and that carbon, you see, well, all of these carbons in the hexagon are not drawn out. So this is actually a skeletally bitter formula in the middle, and these carbons especially have hydrogens on them. If you count up the bonds on that bottom yellow carbon here, then it's got 1 up to to the next carbon up there, and it's got a double to the left-hand side carbon, but that's only 3 bonds. So there must be, and there is, a hydrogen sticking off. So you could draw it in. But the whole thing about skeletal formulas is you're trying to be quick, so you won't draw it in unless you need to. So let's make this into 100% skeletal formula, rather than this kind of hybrid thing that you've got here. Well, let's start off with the hexagon. And you've got to draw in the double bonds. Remember, the first bit, it was skeletal anyway. But on this right-hand side, you've got a bond to a carbon atom. We don't draw in the carbon atoms, but we draw in the oxygen that it's bonded to. And actually, in skeletal, you do not have to put in that hydrogen here. So some people will put in a hydrogen there, because sometimes you can put the odd hydrogen in skeletal just to make it really clear what you're doing, but you don't have to, because the whole thing about skeletal is it's quick and you don't need to. So, okay, how do we treat this area on the left-hand side, this CH3? Well, literally just a stick. Just a stick. Because that's the bond between the carbon and the carbon. Because the end of this stick, this bottom end of the stick, the bottom carbon here, because it has nothing else apart from hydrogens on it, you don't need to draw the hydrogens that are bonded to carbon, so you don't. So it's nice and simple, nice and easy. And my advice for the A-level course is just test yourself to use skeletal wherever possible. Okay, you'll get things wrong in the first couple of months, okay? But you'll get corrected on it and you'll get good at it. And once you get good at it, you're going to be so much quicker at your getting onto the organic problem-solving aspects of things, and you'll have longer to solve the problems, and it'll actually help you keep your ideas organised better. So do try skeletal. This skeletal formula is not finished, because we still have this bromine atom that we haven't drawn in, so we're just drawing in the bromine atom. So bond to the bromine, it's not a hydrogen or a carbon, so I need to specify what it is, so I put Br there. So this thing here might look weird, and it definitely looks weird because even to me, because I'm not very good at drawing with these styluses and things, but it's skeletal formula there, and that blue hydrogen is not needed. You don't even need to have that for skeletal, but you're never going to get marked down for doing the odd extra thing on a skeletal formula. The whole point in skeletal formula is it's quick. Okay, let's just move up to looking at structural formulas when you've got something branched. So let's look at this lovely 2,4-dimethyl heptane here. Okay, that's not the displayed formula. Have a little pause and think why it's not a displayed formula. Well done to anyone who realised that these CH3s here, you haven't drawn the bonds to the carbon to the hydrogen, so that is not a displayed formula, because you need every single bond between atoms drawn in a displayed formula. So even that thing, which would have taken a while to draw, is not even a displayed formula. To do the structural formula, so I could write it in a sentence, well, I'd look at what's on every carbon. So let's do the same. So that left carbon is CH3. Lovely. Now this next carbon, it's a carbon, it's got a hydrogen on it, and it's also got a whole CH3 group on it. So open some brackets, put CH3, close those brackets. That shows that the whole CH3 sticks off the carbon that was before it in the bit of skeletal formula. On to the next carbon hydrogen bit. Well, that's just a normal CH2. Beautiful. Okay, so let's write that in. Next one, again, it's a carbon with a hydrogen on it, and also a CH3, a whole CH3 group. So open the brackets, put the CH3. Sorry. My style is not very good on the right-hand side of the paper. And then just finish off with those last two CH2s and a CH3. So these are all in a line. So CH2, CH2. Now you wouldn't go in a dodgy angle. It's just that I'm run out of space here. CH3, because the last carbon's got CH3. So again, you see that was a little bit quicker than drawing the display, but it wasn't massively quick. So skeletal is okay. So how do we draw the skeletal? Well, you've got the end of the chain going to the next atom. This atom has a hydrogen on it that we don't draw, but it does have a CH3 on. How do I draw a CH3? Just a line to a dead end, because that carbon is only bonded to hydrogen. apart from this carbon. So you draw the line from the carbon-carbon bond, that's it. And then the rest of the chain is coming from this carbon, remember? So this carbon here goes to the next one, which goes to this carbon, which now again has a CH3 on, and the rest of the chain on, which goes to that carbon, which is bonded to another carbon, which is bonded to the end carbon. So it should be 1, 2, 3, 4, 5, 6, 7 in a row, which matches the fact it's a heptane derivative. And the 2,4-dimethyl tells you that you've got on the second carbon and the fourth carbon, you've got methyl groups. If you number from the left-hand side, if you numbered from the right-hand side, it'd be 1, 2, 3, 4, 5, 6. So it'd be 4, 6-dimethyl heptane. But by IUPAC, the guys who make all the rules, told us to number so that the numbers are smaller. So if you've got the choice between 4, 6 and 2, 4, you go for 2, 4 because those numbers are smaller than 4 and 6. So 2,4-dimethyl heptane skeletally is lovely and quick to draw. Okay. I'm just going to choose one of these just to show you how things with more heteroatoms. So heteroatom is an atom that is not carbon or hydrogen, so therefore probably has quite a different, I'm not going to use the word electronegativity because you don't know what it is yet, but they're the ones that tend to react a little bit more, those bonds of between carbons and things that are not hydrogen, because of how the electrons aren't shared evenly actually. So we call them heteroatoms, and they're very important because they tend to be the bits that react. But when you've got something in them, then skeletal is something that looks a little bit more complicated. So we've got this ClOC. Now, what's that talking about? Now, there's a few different ways you could imagine a Cl and an O and a C being linked. You might think, oh, Cl to O to C. Okay. And then the next C, and then there's 2 CH4s in a row. Sorry, 2 CH2s in a row. So that'll be a CH2 group. And then the next CH2 group. Now, if we look at this left-hand side end now, well, it works in terms of chlorine having one bond. It's in group 7, it wants one bond. Oxygen's has 2 bonds. Group 6 wants 2 bonds. Carbon's group 4 wants 4 bonds, but you've only got 1, 2 bonds. So this is not the correct group because it doesn't work for carbon. So there must be another way to arrange these 3 atoms around that carbon to make it everything obey the number of bonds that it wants. So I'll have a pause and have a little think about how you could do that. Okay, so how you actually do that is, if you think about the carbon, if you make it double bond to oxygen, that gives oxygen the 2 bonds it wants, and carbon 2 bonds. Now, if you link that carbon to the chlorine, then that gives the carbon its 3rd bond, then the next ones goes to the CH2. CH2. And on the other end, the COCl corresponds to the same group again. COCl. So this isn't the displayed formula. That is the displayed formula actually. Oh, look at on my left-hand side. I've drawn the Cl wrong. The Cl chlorine should be Cl like normal. You don't need to draw it backwards because it's only one atom. So my apologies there. That is actually a displayed formula because every single bond is shown. But to get it into skeletal formula, then I think, okay, well, the end actually, well, the carbon, I don't draw the carbon in, but I still need to draw the chlorine in because it's not a carbon hydrogen. I still need to draw my double bond to oxygen in because oxygen's not a carbon hydrogen. Now this carbon, sorry, highlighter, go, highlighter. That carbon bond, well, that's just a normal stick. And then it goes to another carbon that's got 2 hydrogens and another carbon on. So I just draw the bond to the next carbon, ignore the hydrogens. And those 2 hydrogens, they come off there, and now I draw another bond to the final carbon on the end. And the final carbon on the end has lots of stuff on it. It's got double bond to oxygen and a single bond to chlorine. On the right-hand side of my touchscreen never really likes it very much, so apologies here. That's a chlorine. So the skeletal there, you see, actually has got quite a lot of bonds on it, but it's still lots quicker to draw than the displayed formula, or the structural formula is maybe quicker to write, but the structural formula, you have to think quite a lot as a chemist about how these bonds are arranged in the first place, whereas the displayed formula tells you how the bonds are arranged. So displayed formula, sorry, not the displayed formula, the skeletal formula, this right-hand side skeletal formula. Skeletal formula for me is what I'd like you to take out of this class. If you can do skeletal formulas and you or not perfectly, but if you can have a go at doing skeletal formulas and take that into your A level, then I promise you it will save you a lot of time in the long run, even though it'll be more time consuming in the short run as you get used to it. Okay. I think there should be details of a task to do on Teams, and also details of the mark scheme to check through that task, all about different formulas.